I am Professor E.O. Efan. I welcome you to lecture series on randomized complete block design. Lecture 1. Introduction. In a randomized complete block design, the experimental units are grouped into blocks of equal size. The units within each block are homogeneous. The blocks are pairwise heterogeneous. That is, variance between blocks is greater than variance within blocks. Randomization is restricted within block. The layout of randomized complete block design. Suppose we wish to compare the effect of care treatment applied to n experimental unit. And suppose that n units are grouped into B blocks of care unit each. Then n is equal to B times care. Let Yij be the observation for treatment J in block I. Then the layout of a randomized complete block design is as shown below. Here is the layout for the randomized complete block design. In this layout, observe that the blocks are arranged in rows. This is block 1, block 2 to block B. And the treatment are arranged in columns. This is treatment 1, treatment 2 to treatment care. Y11 is the observation for treatment J in block 1. Y12 is the observation for treatment 2 in block 1, and so on. This column is for block I total, that is Yi dot represent block I total. So this is block 1 total, block 2 total to block B total. This row represents treatment J total, that is Y dot J. So this is treatment 1 total, treatment 2 total to treatment care total. Y dot dot represent the grand total. The model. The linear statistical model for the randomized complete block design is as follows. Yij equal to mu plus beta I plus tau j plus Eij for I running from 1 to B and j running from 1 to k, where, as defined before, Yij is the observation for treatment J in block I. Mu is the overall mean. Beta I is the effect of block I. Tau j is the effect of treatment J. Eij is the random error of observation for treatment J in block I. 3 cases are involved. Case 1, fixed effect model. Case 2, random effect model. And case 3, mixed effect model. We shall consider only the first case here. The second and the third cases are treated under our lectures on the general 2 factors factorial experiment. The fixed effect model. The assumptions for the fixed effect models are: Assumption 1. The treatment levels and the block size are considered fixed. Assumption 2. The sum of the treatment effect is 0. That is, sum of tau j as j goes from 1 to k is equal to 0. Assumption 3. The sum of block effect is also 0. That is, sum of beta I as I goes from 1 to k is equal to 0. Assumption 4. The random error component Eij is approximately normally and independently distributed with 0 mean and constant variance sigma squared. Estimation of parameters. The parameters are estimated by the method of least squares. That is, we estimate the parameters mu, beta I, and tau j. That will minimize the sum of squares of errors. The sum of squares of errors is S equal to sum as I goes from 1 to b, sum as j goes from 1 to k of Eij squared. This is equal to sum as I goes from 1 to b, sum as j goes from 1 to k. From our model, Eij is Yij minus mu minus beta I minus tau j, then all squared. To obtain the estimate of mu, first we have to differentiate partially with respect to mu and then equate to 0. To do that, the power 2 here is brought down, and then we differentiate the expression inside the bracket with respect to mu and multiply by that, and the derivative is minus 1. So differentiating partially with respect to mu, this will give us minus 2 sum as I goes from 1 to b, sum as j goes from 1 to k of Yij minus mu minus beta I minus tau j equal to 0. If we divide both sides of this equation by minus 2 and then opening this bracket, this will then give us sum as I goes from 1 to b, sum as j goes from 1 to k of Yij, that is this sum, then minus sum as I goes from 1 to b, j from 1 to k of mu, that will give us minus bk mu. Then minus sum as I goes from 1 to b, j from 1 to k of beta I, that will give us k sum beta I as I goes from 1 to b. Then minus sum as I goes from 1 to b as j goes from 1 to k of tau j. That will give us minus b sum of tau j as j goes from 1 to k. Then we equate this to 0. By our assumption, sum of beta I as I goes from 1 to b is 0. Sum of tau j as j goes from 1 to k is also 0. Then using our dot subscript notation, the first sum here is y dot dot minus bk mu, then equal to 0. Solving for mu, this will give us the estimate of mu, which is mu hat, equal to y dot dot all over bk, and this is equal to y bar dot dot, which is the grand mean. Next, to obtain the estimate of beta I, we differentiate partially with respect to beta I and then equate to 0, and that will give us this. Partial derivative of s with respect to beta I is equal to minus 2 sum as j goes from 1 to k of Yij minus mu minus beta I minus tau j equal to 0. Notice that one of the summation sign here is dropped. That's the one involving I is dropped because the derivative is with respect to beta I. Now, if we divide both sides of this equation by minus 2 and then open this bracket, this will become sum of Yij as j goes from 1 to k minus sum of mu as j goes from 1 to k, and that will give us minus k mu, minus sum of beta I as j goes from 1 to k, that will give us minus k beta I, minus sum of tau j as j goes from 1 to k. Then we equate this to 0. Again, by our assumption, this sum of tau j as j goes from 1 to k is equal to 0. So this equation will now become this. Using our dot subscript notation, this sum is yi dot, then minus k mu minus k beta I equal to 0. To obtain the estimate of beta I, we have to make beta I the subject of formula and then substitute for mu. This will give us beta I hat equals to yi dot all over k minus y bar dot dot, and this is equal to yi dot all over k is y bar I dot, then minus y bar dot dot. So this is the estimate of our beta I for I running from 1 to b. Finally, to obtain the estimate of tau j, we have to differentiate partially with respect to tau j and then equate to 0. That will give us partial derivative of s with respect to tau j is equal to minus 2 sum as I goes from 1 to b of yij minus mu minus beta I minus tau j equal to 0. Again, notice that the summation sign involving j is dropped because our derivative is with respect to tau j. Now, if we divide both sides of this equation by minus 2 and then open this bracket, this will become sum as I goes from 1 to b of yij minus sum of mu as I goes from 1 to b is b mu minus sum of beta I as I goes from 1 to b minus sum of tau j as I goes from 1 to b is b tau j equal to 0. Again, by our assumption, sum of beta I as I goes from 1 to b is 0, and using our dot subscript notation, this equation will now become y dot j minus b mu minus b tau j equal to 0. Making tau j the subject of formula, we obtain the estimate of tau j as tau j hat is equal to y dot j over b minus y bar dot dot, and this is equal to y bar dot j minus y bar dot dot. So y bar dot j minus y bar dot dot is the estimate of our tau j for j going from 1 to k. The hypothesis. The hypotheses of interest in a randomized complete block design experiment are set up as follows. Hypothesis 1. The null hypothesis is tau j is equal to 0 for all j. We are testing this against the alternative hypothesis that tau j is not equal to 0 for some j. The hypothesis 2, we are testing the null hypothesis beta I equal to 0 for all I against the alternative hypothesis beta I is not equal to 0 for some I. Test procedure. The appropriate test procedure for this hypothesis is ANOVA, that is analysis of variance. The ANOVA rationale. ANOVA consists of partitioning the total variability into its component part. One way of doing this is by substituting for the parameters and errors estimate in the model. First, we obtain the estimate of the error as Eij hat is equal to Yij minus mu hat minus beta I hat minus tau j hat. This is equal to Yij minus, we recall that our mu hat is y bar dot dot minus our beta I hat is y bar I dot minus y bar dot dot, then minus our tau j hat is y bar dot j minus y bar dot dot, and this will then give us Yij minus y bar I dot minus y bar dot j plus y bar dot dot. Notice that when you open the bracket, this one will cancel this. This minus will change this one to plus. So this will then give us this expression. So this is the expression for the estimate of our error. Now, from our model, we can rewrite our model as yij minus mu hat equals to beta I hat plus tau j hat plus eij hat. That is yij minus y bar dot dot equal to y bar I dot minus y bar dot dot plus y bar dot j minus y bar dot dot plus the estimate of the error, which is yij minus y bar I dot minus y bar dot j plus y bar dot dot. Now, squaring both sides of this equation and summing over I and j, we will obtain the following. On the left hand side, we have sum as I goes from 1 to b, sum as j goes from 1 to k of yij minus y bar dot dot all squared equal to squaring. There are three terms here on the right hand side, so squaring this and summing, that will give us sum as I goes from 1 to b of k times y bar I dot minus y bar dot dot all squared plus squaring the second term and summing, that will give us sum as j goes from 1 to k of b times y bar dot j minus y bar dot dot all squared plus squaring the third term and then summing, that will give us sum as I goes from 1 to b, sum as j goes from 1 to k of yij minus y bar I dot minus y bar dot j plus y bar dot dot all squared. That is what you have on the sum of squares on the left hand side. Here is sum of squares for total, that is the total variability, is equal to this first term here is the sum of squares of block, that is the sum of squares for block denoted by SSB. The second term here is sum of squares for treatment, while the last term here is sum of squares for error. This is so since the three cross product terms vanishes. Please note, in the process of squaring both sides of this and summing, there are some product terms, there are three of them in numbers, so we can always show that these product terms all vanishes. So that is why we arrive at this expression here, where sum of squares for total SST naught is equal to sum as I goes from 1 to b, sum as j goes from 1 to k of yij minus y bar dot dot all squared. And this we can show to be equal to sum as I goes from 1 to b, sum as j goes from 1 to k of yij squared minus the correction factor CF. Sum of squares for treatment, that is SST, is equal to sum j from 1 to k of b times y bar dot j minus y bar dot dot all squared. And this we can show to be equal to sum as j goes from 1 to k of y dot j squared over b minus the correction factor CF. Sum of squares for blocks, that's SSB, is equal to sum as I goes from 1 to b of k times y bar I dot minus y bar dot dot all squared. We can also show that this is equal to sum as I goes from 1 to b of yi dot squared over k minus the correction factor CF, where the correction factor CF is equal to y dot dot squared all over n, and we recall that n here represent bk. And finally, the sum of squares for errors SSE is equal to sum as I goes from 1 to b, sum as j goes from 1 to k of yij minus y bar I dot minus y bar dot j plus y bar dot dot all squared. And this can easily be obtained by subtracting the sum of squares for block and sum of squares for treatment from the sum of squares for total. Degrees of freedom for sum of squares. There are n total observations, so degrees of freedom for sum of squares for total is n minus 1. There are k levels of treatment, so degrees of freedom for sum of squares for treatment is k minus 1. There are B blocks, so degrees of freedom for sum of squares for block is B minus 1. Degrees of freedom for sum of squares for error is obtained by subtracting degrees of freedom for sum of squares of treatment and degrees of freedom for sum of squares of block from that of total. That is n minus 1 minus k minus 1 minus b minus 1. That will give us n minus k minus b plus 1. Since n is equal to bk, this can be factorized into k minus 1 times b minus 1. Distributional properties of sum of squares. 1. Sum of squares for total divided by sigma squared is approximately chi-square with n minus 1 degrees of freedom. 2. Sum of squares for treatment over sigma squared is approximately chi-square with k minus 1 degrees of freedom. 3. Sum of squares for blocks divided by sigma squared is approximately chi-squared with b degrees of freedom. 4. Sum of squares for errors over sigma squared is approximately chi-squared with k minus 1 times b minus 1 degrees of freedom. Mean square and F statistics. 1. The mean square for treatment is equal to sum of squares for treatment over degrees of freedom k minus 1. 2. Mean square for blocks is equal to sum of squares for blocks all over b minus 1. 3. Mean square for errors is equal to sum of squares for errors all over k minus 1 times b minus 1. 4. The expected mean square for treatment can be shown to be equal to sigma squared plus b times sum as j goes from 1 to k of tau j squared all over k minus 1. The expected mean square for blocks can also be shown to be equal to sigma squared plus k times sum as I goes from 1 to b of beta I squared all over b minus 1. 6. The expected mean square for error can be shown to be equal to sigma squared. Under the null hypothesis H0, that is tau j equal to 0 for all j, one can show that the expected mean square for treatment is equal to the expected mean square for error. And that will imply that the statistics F0 is equal to mean square for treatment all over mean square for error is approximately f with k minus 1 numerator degrees of freedom and k minus 1 times b minus 1 denominator degrees of freedom. 2. Under the null hypothesis beta I equal to 0 for all I, expected mean square for blocks is equal to the expected mean square for error. And from here we can compute the F statistics F0 to be mean square for blocks all over mean square for error, and this has F distribution with b minus 1 numerator degrees of freedom and k minus 1 times b minus 1 denominator degrees of freedom. The critical region of the test. Notice that 1. Under the alternative hypothesis H1, that the expected mean square for treatment is greater than the expected mean square for error. Thus, the null hypothesis H0 should be rejected if F naught is greater than F alpha with k minus 1 numerator degrees of freedom and k minus 1 times b minus 1 denominator degrees of freedom. 2. Under the alternative hypothesis H1, that the expected mean square for blocks is greater than the expected mean square for error. Thus, H0 should also be rejected if F0 is greater than F alpha with b minus 1 numerator degrees of freedom and k minus 1 times b minus 1 denominator degrees of freedom. ANOVA table. The above test procedure is usually summarized in an ANOVA table as shown below. Here the first column is for source of variation. Under source of variation we have treatment, blocks, error, and then total. Then the second column is for degrees of freedom. Degrees of freedom for treatment is k minus 1, for blocks is b minus 1, for error it is k minus 1 times b minus 1, and for total is capital N minus 1. The next column is for sum of squares. We have sum of squares for treatment, sum of squares for blocks, sum of squares for error, then sum of squares for total. Then the next column is the mean square, the column for mean square. Mean square for treatment, which is obtained by dividing this one by this. Mean square for blocks, this divided by this. Mean square for error, this divided by this. Then the last column is for F statistic, F naught. So for treatment, we divide mean square for treatment by mean square for error, and then for blocks we divide mean square for blocks by mean square for errors. Thank you for watching. Keep on watching.